So as you can see that this meeting is recorded, and I'm going to talk about uh, what we are trying to study in the second law of thermodynamics. So in the past, we looked at the steady flow processes. We looked at the significance of minus VDP. We looked at the relationship between the PdV work and minus VDP work. We worked out quite a few problems. Then we moved on to the tricky problem wherein we had to find out the enthalpy, and then we looked at the enthalpy of evaporation, and then at the end we started talking about the second law of thermodynamics. So in the second law of thermodynamics, as you know, this second law came into existence to somehow overcome the limitations of the first law of thermodynamics. Second law of thermodynamics talks about following important things. First and foremost, it talks about the quality of energy. In other words, first law says work and heat, they are interchangeable, but it doesn't talk about the grade or the quality of energy. On the other hand, second law of thermodynamics talks about the quality of energy. Work is a higher quality energy than heat. That's why conversion from work to heat is easier, but from heat to work incurs significant losses. The next thing that is important is there are directionality. So basically, we know that the heat will flow from high temperature to low temperature on its own. But if you want to reverse that flow of energy from low temperature to high temperature, you have to spend some energy. And that is where the second law of thermodynamics comes in the picture. There are two statements of second law of thermodynamics. One is Kelvin Planck, and the second statement is the Clausius statement. Those two statements are essentially equivalent. They are the same, but the interpretation is slightly different. In the case of Kelvin Planck statement, this statement deals with heat engine. Very simply, it says you cannot have a heat engine with 100%. So you can't have a heat engine that will take all the heat possible and convert everything into work. The heat engine has to reject some heat. Kelvin Planck's statement is related to heat engines. On the other hand, Clausius' statement is associated with heat pumps or refrigerators. Clausius' statement says that you can't have heat transfer from low temperature to high temperature on its own. You will have to spend energy. And that's these two statements, they are equivalent. And we talked about this equivalence or similarity of these two statements earlier. So now we are going to talk about something called as the Carnot cycle or Carnot refrigerator. This is purely a thought exercise, and that talks about a heat engine, a hypothetical heat engine, or a hypothetical refrigerator that works in between two temperature ranges. And that's what we are doing, and we will work out few problems based on the Carnot cycle. And then we will work out a few problems. And this chapter is sort of the background information or fundamentals to the next chapter. That entire chapter is on entropy. And if time permits, we will talk about entropy today. If or we can start talking about entropy in next class. So the basic premise of second law is to identify the direction and the quality of energy. So even though we know that heat and work are interchangeable, work is high grade and heat is low grade. So which means heat to work, you are going to have losses. And that's what it means by application of second law of thermodynamics. We looked at this briefly in last class. So what are the major applications of the second law of thermodynamics? Second law of thermodynamics talks about the direction. It talks about the quality and quantity. Unlike first law, where the first law is only concerned with the quantity, second law talks about the quality. And second law of thermodynamics provides the theoretical limits that can be used for determination of thermodynamic efficiencies or coefficient of performance of a heat engine or a refrigerator. And that is the major advantage of the second law. And second law leads to the concept of third law, which is or sometimes also called as the law of entropy. And we will talk about it in today's class or in the next class. Moving on. So here is the concept of reservoir. The concept of reservoir is simple. No matter how much energy is added or removed from this reservoir, that is either source or sink, the temperature does not change. That is the fundamental principle of reservoir. Why do we need reservoirs? Reservoirs are needed so that we can apply the thermodynamic principles, the temperature scales, and the limits, and derive the expression for efficiency in terms of temperature differential. Now, here is a classic example. So consider the internal combustion engine or IC engine, which is the engine used for cars, trucks, generators. That engine is converting heat to work, and that heat to work conversion is achieved by using a working fluid such as air fuel mixture. The fuel gets burned, and then as the fuel is burned, the temperature increases, the heat is converted to work, and some part of heat is rejected to the surrounding. And that's exactly what is shown in the slide that we have in front of us. You have a high temperature source which has been denoted as TH. You have a low temperature sink which is denoted as TL. And you have a heat engine that is operating between these two limits. So you have TH, you have TL, there is Q in that is coming to the engine, Q out that is coming out of the engine. Please note, heat engine does not store heat. It's not a battery. It only converts heat to work. So heat engine, if I want to write down the energy balance, and I want to emphasize on this, so energy balance is something like Q is going in, part of this Q in is converted to work, and part of it is rejected. So the energy balance equation is Q in is equal to work done plus Q out. And efficiency is always work done divided by Q in. And remember this equation. Now, a classic example is a steam power plant. And if you drive around Val Vista, I think at Val Vista and Werner intersection on the southeast side, you will see SRP power plant. It's a steam power plant, but what they use natural gas as a fuel to do the external combustion. So again, the principle is simple. You have water that is pumped to the boiler, and using natural gas or any other means like coal or some other nuclear reactor, the heat is generated. That heat heats the water, the water gets converted to steam. Steam, high pressure, high temperature steam is expanded in turbine, and you get work out. This turbine shaft is attached to the generator, and the electrical power is generated. And then low pressure, low temperature steam is exhausted in the condenser, and in condenser the steam cools down and the steam gets converted back to water, and that water can now be pumped again to the boiler, and this process can continue. So that is how a steam power plant works. And we talked about the thermal efficiency a minute ago. So for thermal efficiency, you will always write it in terms of energy balance and the work output divided by the heat input is the equation for thermal efficiency. Now, one thing I just want to tell you is when you have something like a furnace, and if you have a sink, we assume them to be reservoirs, and we assume them to be at constant temperature of TH and TL. So in other words, I can write this equation down as QL is proportional to TL, QH is proportional to TH, and this equation for efficiency can be written as 1 minus TL divided by TH. And this equation is possible because of the thermal reservoir assumption, which means source is going to be at high temperature. That temperature is going to be at constant temperature. Sink is going to be at low temperature, and that temperature will also be constant. So now next thing is it possible to recapture the energy? The answer to that question is you can try to recapture or harvest the energy, but many times it is not possible to harvest energy because second law of thermodynamics dictates that you need to have some heat rejected so that engine can work in a cyclic fashion. So that is super important and please keep that in mind. And this is the example that we talked about in last lecture. And this example is and thank you for your patience. And what I would do is I would try to, if I get disconnected, please let me know, and then I will try to call back again. Okay. So we have been talking about the second law of thermodynamics, Kevin Planck statement. This statement again says the 100% efficiency is not possible. And when 100% efficiency is not possible, at that time, somehow you try to harvest as much energy as possible, but many a times we can't harvest more energy because we would otherwise be in violation of the second law of thermodynamics. Now let's talk about the refrigerators and heat pumps. So how does a refrigerator or heat pump work? And I'm gonna try to give you a very simple example. So, so how does an air conditioning or refrigerator work? So what I want you to visualize, this is a thought exercise. Consider that you have a bottle of rubbing alcohol. Okay. And as you know, this bottle needs to be capped, otherwise the rubbing alcohol would evaporate. And maybe you are using it for some sort of cleaning or sanitizing purposes. You pour a little bit of alcohol on your hand or on your palm. So imagine that you pour little bit of rubbing alcohol on your hand, on your palm. What's going to happen is this rubbing alcohol is going to evaporate. And as it evaporates, it's going to absorb the heat of evaporation from your palm. So as rubbing alcohol evaporates, it absorbs heat from palm. What is the consequence of this? Your palm feels cool. Now, if I were to continue this process again and again and again and again and again and again, then what could happen is I could drop the temperature of your palm down continuously. But what it means, it requires infinite amount of rubbing alcohol, and I would continuously have to pour it on your palm. But what I could do is, alternatively, I could recapture this vapor. Somehow, I want you to visualize something like this. What I would do is, I would recapture this vapor and use a compressor. Okay, this is a compressor, not a pump. I will use a compressor to compress this vapor. Now, as I'm gonna start compressing this vapor, the pressure is going to increase. What it means, and as you know, as you increase the pressure, the gases get converted to liquid. So what's going to happen is, as you start compressing this, these rubbing alcohol in the vapor state, so this is vapor state, will get converted to liquid state at the exit of the compressor. But this liquid will be at high temperature and high pressure. So this liquid will be at high temperature. So this will be at high temperature and high pressure. What I'm going to do is, I'm going to pass this vapor through a condenser coil. So some sort of coil that would cool down the liquid. So this is called as the condenser. And then once I have the liquid that goes through condenser, the pressure will be high, okay, but the temperature will be low. And then think about it, this liquid at low temperature but high pressure can be stored in some sort of reservoir. And then what I would do is, I would again repeat this pouring process. I would continuously pour, but then in this process, I'm actually recapturing the vapor. And assuming if I'm able to capture the entire mass, I would have the working fluid, this is rubbing alcohol, circulating through the system, and I don't need an infinite reservoir to fill this tank. So I will try to be more smart. And what I would do is, I would add an expansion valve or a throttling valve over here. So this process of pouring liquid is nothing but sort of a throttling process, which means the high pressure liquid is going through a very teeny tiny opening, and in that case the pressure drops down. So the pressure drops down, temperature drops down, and when it comes in contact with the substance that needs to be cooled, it can absorb the heat and get converted. This is a very fundamental refrigeration cycle. So let me start with the components of the refrigeration cycle. You are going to have an evaporator. The evaporator is nothing but a heat exchanger. So you have an evaporator and it will be a heat exchanger. This heat exchanger evaporator is connected to a compressor. So this is connected to a compressor. This is called as the evaporator. So this is an evaporator. Then this compressor is connected to another heat exchanger, and that heat exchanger is called as the condenser. So this is the condenser. And at the end of the condenser, you could have a reservoir or a strainer, and from the strainer there is something called as the expansion valve or a throttling valve or a capillary tube. So you have an evaporator, you have a condenser, this is the condenser, you have a throttling valve, and you have a compressor. Now, I want you to be very clear. If you look at your air conditioning system, whether you look at your car air conditioning system or whether you look at your house air conditioning system, the compressor and condenser, they are placed outside the area to be cooled, because this is where the heat rejection is going to take place. So in condenser, high pressure, high temperature liquid is cooled. So this is where the heat is rejected. And this is actually your system where you should be focusing to cool things down. So the evaporator is inside your house with an air handler. Throttling valve is typically inside the house in near the air handler, but the big boxes that you see outside, they have a compressor, a condenser, and the fan that circulates the air around the compressor and condenser to cool them down. Air conditioning system is very simple to fix and diagnose. There are only four components, essential four components: compressor, condenser, throttling valve, and evaporator. But sometimes they add a strainer, sometimes they add an accumulator just as a safety precautions to take away the impurities and then make sure that the refrigerant is stored at some location. So now with this basic concept, let's look at the, the schematic of a refrigeration system. So you have an evaporator that is inside the refrigerated space. This is the space that we want to cool down. Then here, the working substance absorbs heat from the space or the system, and this working substance is evaporated, and this refrigerated space drops down in temperature. This refrigerant vapor is compressed inside the compressor. I want you to understand this is vapor. This is compressed and this becomes liquid. So you have the vapor. That vapor is compressed. After compression, you have high temperature, high pressure liquid. This liquid passes through condenser. So the pressure remains high. So here pressure is high, but temperature is also high. And I want you to note specifically, this temperature is 60 degrees Celsius. In other words, this temperature is higher than the surrounding medium like kitchen air. That's why the heat is rejected into the surrounding, which means if you look at the coils that are at the back of your refrigerator, there are condenser coils. If you touch those coils, they will be slightly at higher temperature because that is where the working fluid is rejecting its heat to the surrounding. Then once it goes through the condenser, you have high pressure. So high pressure, but the temperature drops down. Temperature is lower. Please note, temperature is not the lowest, but temperature is lower. Then this high pressure and lower temperature liquid. It is very important to know that here again it is liquid. Get passed through a very teeny tiny opening, and that exactly where the liquid gets converted to low temperature vapor. So here you have low temperature, low pressure vapor. So here low pressure and low temperature. And what happens is this low temperature, low pressure vapor absorbs heat from the evaporator and then back and takes that heat all the way to the compressor. This is exactly a simple air conditioning and refrigeration system works. One thing I want you to note, and this is very important, that the high pressure here, high pressure is same on either side of the compressor, either side of the condenser. This is the same pressure. Low pressure is the same on either side of condenser. So I don't know if you have seen those air conditioning and refrigeration techs. What they do is they have a pressure gauge, a differential pressure gauge. They connect those, that is called as the manifold gauge. There are two pressure gauges and they connect these manifold gauges onto the either side of compressor. And then along with that, they have the thermocouples. Those are attached to the either side of the compressor. With just manifold gauge, you can diagnose the entire air conditioning and refrigeration system. What you need to check. So what are the typical issues when the cooling is inadequate? When the cooling is inadequate, that means the pressure on the high side is not high enough, or pressure on the low side is not low enough. If there is a refrigerant leakage, then there is a loss of pressure. The compressor would lose pressure if the refrigeration is low. If there is an impurity or an obstacle, which is very common with the old air conditioning system, or if you have clogged expansion valve, the high side pressure is very high and low side pressure is no pressure because the refrigerant is not flowing. And in that case, compressor heats up, there is a thermal switch and the compressor gets turned off. This compressor is completely sealed and is called hermetically sealed compressor. Hermetically sealed compressor. And the reason this is completely sealed because refrigerants are very notorious. They can leak through a very teeny tiny opening. Because think about it, we are at 800 kilopascal, which is 8 bar, which is 8 times the atmospheric pressure. So that's a very high pressure to deal with. On the other hand, we are also at 120 kilopascal, which is 1.2 bar, which is again a quite high pressure compared to the atmospheric pressure. Which means if there is a teeny tiny opening, say if you have a crack in the condenser or if you have a crack in the evaporator, believe you me, all that refrigerant will will get out of this system in no time. That's why you use special O-rings, those are of green color, and special lubricants and special sealants to seal this closed system. Typically, the amount of refrigerant inside the system is very small. It's sometimes very few ounces. But that fluid is continuously worked upon at a very high speed. The compressor can run anywhere between 1200 to 3000 RPM. So the number of cycles are very high. And this continuous cycling of the refrigerant is actually creating this refrigeration that we are so used to. So if you take air conditioning and refrigeration class, we will talk a lot more detail in different types of air conditioning systems. So there is vapor. This is called as vapor compression system. So this is vapor compression. There is another system which is called as uh, absorption refrigeration system, wherein what you do is the refrigerant is absorbed rather than compressed, and in that process you create the refrigeration effect. But I just want to tell you something real quick. In the aircrafts, vapor compression system is not used. The air conditioning and refrigeration that is used in aircraft is called air refrigeration system. And here is the reason for air refrigeration system. As the aircraft is flying through the atmosphere, it's at very high speed. And at high speed, the air that is impinging on the aircraft structure is getting compressed because that high speed air suddenly loses all the velocity. And according to Bernoulli's principle, if you stop a high moving fluid, suddenly the pressure is going to shoot up. So what you have is you have compressed air available to you free of cost when you are flying an aircraft. So what they do in that case, they take this compressed air, cool it down, and just throttle it or run it that through expansion valve, and then that is expanded in the cabin, and that is how the air conditioning works in the aircraft. That's why, and this is an important observation, when the aircraft is on the ground, the air conditioning is not working very efficiently. And that's why the flight attendants tell us, hey, close the window so aircraft interior doesn't get heated up. Because when the aircraft is stationary, you don't have compressed air. So air refrigeration does not work. There could be some small supplemental vapor compression system for essential systems, but typically air refrigeration is the main source of air conditioning in the aircrafts. So as soon as aircraft is on the ground, the inside temperature is higher, and as the aircraft takes off and it reaches the cruising altitude, at that time the air conditioning is much more efficient. As a matter of fact, the jet engines are more efficient at elevated altitude because the air that is coming inside the engine is sort of pre-compressed because of the high-speed air impinging on the jet engine compressors. And that's why when the aircraft is flying, it's the most efficient. Okay, so I hope that this will pique your interest in air conditioning and refrigeration. It's a very simple system to work and diagnose, and there are different types of air conditioning systems. And we will, in today's class, we will look at solving problems on the refrigeration systems. So before I proceed further, I just want to make sure that everyone understood the air conditioning and refrigeration principle, vapor compression cycle. Any questions? Everyone understood air conditioning, refrigeration cycle? I'm looking at my chat window to get any feedback. Okay, moving on. For the air conditioners, we don't have concept of efficiency because typically efficiency is less than 100%. For air conditioners, we have the concept of coefficient of performance. And what is coefficient of performance? Coefficient of performance, the simple definition is desired output divided by required input. So in the case of refrigerators, we are focusing on rejecting absorbing heat. So if we are looking at heat absorption, then my desired output is QL. And so in the case of refrigerators, I'm going to focus on QL. This is for refrigerators. On the other hand, in the case of heat pumps, I would be focusing on QH. So this is heat pump. So depending upon whether you are using the system as a refrigerator or heat pump, the coefficient of performance is defined slightly differently. So coefficient of performance for the refrigerator is the desired effect, which is QL divided by WN. Coefficient of performance in the case of heat pump is given as QH divided by work in. So I want everyone to be absolutely clear about the definitions of coefficient of performance. Coefficient of performance for the refrigerator is QL divided by WN, because QL is the desired output. In the case of heat pump, QH is the desired output. Now again, using the concept of source and sink, I'm going to say TH is the temperature of my high temperature sink, and TL is the temperature of my low temperature source. So this expression can now be written as QL divided by QL minus, QH minus QL. This can be written as QH minus QL. So QL is proportional to TL. QH is proportional to TL. And this equation comes TH minus TH minus TL. Now, I want you to verify this very carefully. Coefficient of refrigerator plus coefficient of heat pump is equal to, tell me what is on the right hand side. Or let me be a little bit careful here. So COP of heat pump and COP of refrigerator. So COP of refrigerator plus COP of heat pump, what do I get? If you look at this equation is going to become minus TL plus TH divided by TH minus TL. So I get 1. This is an important equation that you should remember. So COP of heat pump minus COP of refrigerator is equal to 1. In other words, coefficient of performance of the heat pump is 1 plus coefficient of performance of the refrigerator, assuming same system is used as heat pump and refrigerator. Now let me ask you this question. So what you want to do is you want to heat a space, okay? And you have 2 options. Either you can use a heat pump or you can use an electric heater. So let me ask you this question. So it's a design question. So I have this space that needs to be heated. So this needs to be at high temperature. And I have 2 options. Either I can use a heat pump or I can use an electric heater. Out of these 2 options, which one would you choose and why? Now let me, if you think we should be using heat pump, just say A in the chat box. If you think we should be using electric heater, say B in the chat window. So the question is, should I be using heat pump or should I be using the electric heater? I just see one answer. Now, let me ask you this. Which will be more efficient, heat pump or electric heater? Which will be more efficient? So, more which will be more efficient? Now, one thing let me tell you here, heat pump is always more efficient because COP is always greater than 1. Electric heater is less efficient because electrical work is converted to heat. So heat pump is more efficient than electric heater, but uh, the problem with heat pump is, think about it like this. You will have to place the condenser inside and you will have to place the evaporator outside, and then there will be compressor somewhere here. So this is the evaporator and this is the condenser. What should happen is the surrounding temperature here should be lower than the evaporative temperature so that the heat, so surrounding temperature should be higher. Surrounding temperature should be higher than the evaporative temperature so that the heat can flow inside. Because that is how we want to heat the system. On the other hand, you could have a resistance heater and then you can send the electrical current V times I, and depending upon the efficiency of the coil, that electrical work will get converted to heat. But dollar to dollar, heat pump is more efficient than electric heater. But if the outside temperature is too low, then heat pump will not work. So let me state this down. If outside temperature is too low, heat pump will not work. Because thermodynamically, this is what is happening. You have this space that needs to be heated. Thermodynamically, how is this gonna happen? You will have surrounding. From the surrounding, you will take heat and inject that into the system. So you have surrounding, and this is system. And what you're gonna do is you are going to take the heat from the surrounding and inject it into the system. To be honest with you, if this is inside temperature and if this is outside temperature, you are actually causing the heat flow from lower temperature to higher temperature. So this is the direction of heat flow. And since you are creating the heat flow from the low temperature to higher temperature, you need to do work. That's why you have the compressor and everything that is making that is causing this energy transfer. So always remember this: if you have a heat pump, it will be efficient, but it will not work at a very low temperature. So here is the equation that we just derived for the heat pump and the refrigerator. COP of heat pump is equal to COP of refrigerator plus 1. Now, nowadays, what we do is, if you look at the air conditioners and refrigerators, they are defined, the efficiencies are defined in terms of EER, which is called as energy efficiency rating. Energy efficiency rating is nothing but the amount of heat that is removed from the cooled space in British thermal unit. So BTU means British thermal units for 1 watt hour of electricity consumed. And I just want to point this out. This definition is sort of inconsistent because BTU is not an SI unit, but watt hour is. So this is a little bit arbitrary in the sense that we are trying to relate a quantity in the SI unit with the quantity in metric, in quantity in English units. So you want to be a little bit of careful. EER is the amount of heat that is removed in BTUs for 1 watt hour of work or electricity consumed. And that's the point that I was trying to make is explained here. The COP of refrigerator decreases. We decrease in the refrigeration temperature. And it's not, that's why it's not economical to run the refrigerator to a lower temperature than that is needed. Most heat pumps usually have coefficient of performance between 2 and 3. As the heat pumps or refrigerators get older, the losses increase and the coefficient of performance decreases. So sometimes you have air conditioners, refrigerators that are working for 10, 12 years, and then all of a sudden you realize that there is a problem and that the time has come to get a new, more efficient air conditioning system. So now, this is the Clausius statement, and we discussed this in detail, but let's reiterate. It's impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a low temperature to high temperature. In other words, you cannot have a system that will take heat from low temperature and push it onto higher temperature without expanding work. That's why you need to spend electrical energy to run the refrigeration system. On the other hand, if you have a heated hot object, it will cool down on its own. Now, it is very important to realize that just like first law of thermodynamics, second law of thermodynamics is not proved mathematically, but no experiments performed so far have shown that thermodynamic second law is not true. So thermodynamic laws of thermodynamics, they don't have mathematical definitions, but they based on the practice, empirical evidence, and all the experiments performed so far, this law has shown to be true. Now, here is something that we discussed earlier, but again, reiteration. Clausius statement and the, the Kevin Planck statement, both these statements are one and the same. And how do we prove the equivalence of these two statements? So consider a heat engine and a refrigerator that is operating between one source at high temperature and another sink at low temperature. Or you could consider a high temperature reservoir and a low temperature reservoir. Now, if you were to violate one statement, for an example, let's violate Kevin Planck statement, then that statement automatically violates Clausius statement. Since Kevin Planck statement violation leads to violation of Clausius statement, these two statements are considered to be equivalent. Now, how does this violation take place? So look at this, that you have a heat engine. So this is a heat engine and you have a refrigerator. And I'm going to violate the Kevin Planck statement. Violation of Kevin Planck statement is nothing but removal of this link. That means heat engine needs to reject uh, the, the heat. And then what I could potentially do is whatever heat is coming in to the heat engine, all that energy, all that uh, work is being used to run a refrigerator. And when you run that as a refrigerator, it's quite obvious that the Clausius statement is violated, because then the refrigerator doesn't need any external work. So once you do this, notice that there is no work input. So this is a clear violation of Clausius statement, and that tells me that if you have violated the Kevin Planck statement, and then, sorry about the background noise, if you violate the Kevin Planck statement, the Clausius statement automatically gets violated. Now, moving on, let's look at the concept which is called as perpetual motion machine. Now, perpetual motion machine means the machine that is violating the first or second law of thermodynamics. So, and to be honest with you, the perpetual motion machines are not possible. It's not possible to construct a perpetual motion machine. But it's a hypothetical machine wherein what we do is we assume that a machine that there are two types of machines. One is called the perpetual motion machine of first kind, and second one is called perpetual motion machine of second kind. Perpetual motion machine of first kind violates the first law. So it's a machine that creates the energy. And perpetual motion machine of second kind is violates either the Kelvin Planck statement or Clausius statement. So again, these two machines are perpetual motion machines. These are purely hypothetical and they are not possible in actual practice. So this is like a perpetual motion machine of second kind. In other words, you can think about it something like you connect turbine to the pump. Okay, so essentially the work that is coming out from turbine is used to run the pump and heat the boiler, and that is absolutely not possible because you have the irreversibility, you have entropy, you have losses that will decrease the amount of energy that is available that you can use to generate work. That's why the perpetual motion machine of first kind that generates that can create energy, and perpetual motion machine of second kind, which would actually convert work to heat, heat to work without any external aid, that is not possible. So what I'm going to do is I'm going to stop here for 15 minutes. So 15 minutes break. And we will come back at 3 o'clock and continue the discussion. So I'm going to pause recording and we will continue after 15 minutes. So we are going to talk about reversible and irreversible. In the reversible process, it is the process that can be reversed without leaving any trace on surrounding. Unfortunately, purely reversible processes are not possible in actual practice. So imagine it's like you have a process, either it can be compression or expansion. So you can go from point A to B and then go from point B to A following the exact same path. So this is important. So you have, say, P and V, and you are going from point A to point B, something like this. Now what's gonna happen is you are going from point A to point B in this direction, and then you go from point B to point A in the opposite direction. Please note, you are tracing the same path. So this is very important. You are tracing the same path.
So if you are tracing the same path, there is no effect on the surrounding, as if that process did not occur. So, for an example, you have a frictionless pendulum. So, if the pendulum is swinging, is going from point A to point B, there is no dissipation of heat, there is no loss, there is no change in the surrounding temperature. Then it is called as reversible process. Reversible processes are not possible. It's an assumption, but that is the assumption we usually make to make our life as engineers simple. So, and on the other hand, the irreversible process is the process that is not reversible, which means if you were to go from point A to B, and even though you try to go from point B to A following the exact same path, there will be some thermodynamic effect. For an example, there will be some heating, there will be some external adhesion, there will be some external entropy change that will be caused because of this change in the direction. But still, we assume many of the thermodynamic processes are reversible. So, why do we consider processes to be reversible? Because it's an easier approximation. They are easy to analyze. And these processes can be considered as the idealization of the actual process. And many a times, extremely small processes, extremely slow processes can be considered as reversible processes because the heat interaction is minimal. So if you have a compression that is very slow compression that does not increase the temperature of the working fluid, if you have a very slow expansion that does not change the temperature of the working fluid, then that process could be considered as limited as process. Fast processes, the processes that happen relatively quickly, are irreversible processes. And the reversible processes are obviously more efficient than irreversible processes. In other words, if you have an reversible process, if you have a reversible process, the amount of work that is needed to perform the compression would be least. If you have a reversible expansion process, the amount of work that you get out of that is max. So this is extremely important. So reversible processes are the most efficient processes. Now, there are multiple factors that could lead to reversibility, irreversibility. So the, the factors that lead to irreversibility or increase in entropy is friction, then heat transfer, electrical resistance, deformation, and chemical reaction. So these factors that are commonly observed in the physical processes, they cause the, the systems to become irreversible. Now, there are in reversible processes, there are two categories. One is internally reversible process, and the second one is externally reversible process. In the case of internal reversible process, it means the system is reversible inside the boundary, which means all the irreversibilities occur outside the boundary. So this is an important definition. If the system is internally reversible, or the irreversibilities, for an example, friction, heat transfer, chemical reactions, all these take place outside the system boundary. In the case of externally reversible processes, just opposite opposite of what we talked about internally reversible, all the reversibilities are taking place externally. So internally, system is irreversible. So in other words, inside the system boundary, the friction, heat transfer, entropy increase is taking place. But as soon as you cross the boundary, as soon as you go outside, the system is completely reversible. Now, a totally reversible process is there is no irreversibility inside the boundary or outside the boundary. So system and the surrounding, everything, the interaction taking place is reversible. Only then is totally reversible process. Now, this reversible process gives rise to something called as the Carnot cycle. Now, what is a Carnot cycle? Carnot cycle is a hypothetical cycle wherein you have compression and expansion. There are four processes. The first process is reversible isothermal expansion. So consider the piston cylinder shown over here. So you have piston and you have cylinder. And what is happening is the first cycle, I mean the first process, which is from 1 to 2, is a reversible isothermal expansion, which means the temperature is remaining constant. The next process, which is from 2 to 3, is reversible adiabatic expansion, which means the temperature drops down from T high to T low. So, so basically, Carnot cycle comprises of expansion and compression. But there in expansion, there are two parts. First, you have isothermal expansion followed by an adiabatic expansion. Then it reaches point 3. At point 3, you start compressing. So you have isothermal compression and then adiabatic compression. So Carnot cycle comprises of expansion and compression. But expansion is initially it's isothermal, then it becomes adiabatic, then the compression starts. In the first is isothermal and it's adiabatic. Now, believe it, it's a little bit difficult to visualize. So what I'll do is I'm going to try to explain this process. So consider that I have piston cylinder assembly. So I have this piston cylinder assembly. And what's going to happen is basically you have this top dead center when the piston is very close onto the cylinder head side, which is about point A, and this is called as the bottom dead center. Somewhere here, it's a bottom dead center, BDC, where the piston is very close to point B. And piston is going back and forth. It's going from A to B and then going from B to A. Now, as piston is going from A to B, it is expansion. And as piston is going from B to A, it is compression. I want visualize like this. So this expansion process is divided into two parts. This expansion process is divided into two parts. So it goes from A to C and then goes from C to B. So C is somewhere over here. Now imagine this piston goes very slowly. This piston goes very slowly. So it's very slow from A to C. So as this piston is going very slow from A to C, the temperature of the working fluid, which could be air or any other working fluid, is remaining constant. So from A to C, the expansion from A to C, temperature is remaining constant because the process is very slow. And since temperature is process isothermal expansion. Now, what happens is from point C to point B, the process takes place very fast. And this is a weak assumption, but still very fast. So from point C to B, the process temperature is no longer constant, but process is fast. And this is adiabatic expansion. Now, what's going to happen is after this adiabatic expansion, the piston reaches the bottom dead center or point B, and then it starts going from B to A, and it starts doing the same thing. So this compression also occurs in two different stages. First, this compression is very slow. Here, this compression is very slow. So from B to C, so this expansion and B to C, temperature is constant, process is slow, and its isothermal compression. And then from C to A, the temperature is not remaining constant. Process is fast, and it is adiabatic compression. So you have two processes. You have compression and you have expansion, but the expansion occurs in stages. First, you have isothermal expansion, followed by an adiabatic expansion. Then you have isothermal compression, followed by adiabatic compression. So that is how this process is taking place. Now, what I'm going to do is I'm going to write or I'm going to draw this uh, cycle onto a PV diagram. Now, in PV diagram, I want you to note that this cycle is clockwise and this cycle is counterclockwise. So I want this is the cycle for engine. So this is Carnot engine, and this cycle is for Carnot refrigerator or heat pump. And the reason for that is this cycle is clockwise and this cycle is counterclockwise. And keep this in mind whenever you have a thermodynamic cycle, whether it is a PV cycle, whether it's PS cycle, whether it's a PH cycle, or uh, any other cycles, if the cycle is going clockwise, that is the cycle for heat engine. If the cycle is going counterclockwise, that is the cycle for heat pump or refrigerator. What this means is when this cycle is performed, you are gonna get work out, and when this cycle is performed, you would be doing work. So there will be work will be coming out, and in other case, the work will be done on the system. This is extremely important, and I want you to be very comfortable in understanding this, that uh, this this counterclockwise and clockwise cycle is very important. So these are also sometimes as power cycles. So basically, you get power out of the system. Now, Carnot cycle is a completely reversible cycle. What it means is Carnot cycle, when it is performed, it does not leave any trace on the surrounding. It's comprising of completely reversible processes. Again, Carnot cycle is a hypothetical cycle. It is not possible to achieve Carnot cycle or Carnot efficiency or coefficient of performance in actual practice. But for thermodynamic analysis, we start with a Carnot cycle and then add additional constraints and assumptions. So now let's talk about the Carnot principles. So the Carnot principle provides the theoretical maximum efficiencies and coefficient of performance that are possible uh, using the thermodynamic principles. So the Carnot principle is this. If you have an irreversible heat engine, in other words, the heat engine that does not work on Carnot cycle. So irreversible means the the engine not working on Carnot cycle. So if you have an engine that is not working on Carnot cycle, the efficiency of that engine will always be less than the reversible engine, which is Carnot engine. So in other words, Carnot engine, which is a hypothetical engine, is the most efficient engine. The second principle is if you have a reversible engine, which is a Carnot engine, which is operating between the same two reservoirs. And when I say same two reservoirs, the implication is same TH and TL. So you have two same reservoirs, then the efficiency of those two reversible engines, and again, the reversible engines are Carnot engines, they will be the same. So that is the Carnot principle. And this Carnot principle is sometimes used to compare different engines. So here is a simple example. You have an irreversible engine which is less efficient than the reversible engine. You have the third engine which is reversible, which is operating between the same reservoir, which are at TH and TL, and efficiencies of engine 2 and engine 3 is the same. So that's what it means by the Carnot principle. And now there is a proof of the first Carnot principle, and this proof is derived by using some manipulations. So what you do is, if you have a reversible and irreversible heat engine, what you can do is, reversible heat engine can be converted into a refrigerator. And once the reversible heat engine can be converted to refrigerator, what's going to happen is you can connect the work output from irreversible heat engine to the reversible heat engine, and you would realize that you are going to have a combined heat engine and refrigerator that is sending differential work out, working with just one reservoir. So in other words, if you violate the Carnot principle, so how do I violate the Carnot principle? So I'm gonna violate. So I'll. This may need a little discussion because this is not quite obvious. So I'm going to violate violate Carnot principle. So I'm going to say the efficiency of irreversible heat engine is greater than efficiency of the reversible heat engine. In other words, work output, so work from irreversible heat engine is greater than work from reversible heat engine. And that is quite obvious because the reversible heat engine and irreversible heat engine, both of them are working within the same uh, temperature difference, TH and TL. If that is the case, I would convert the reversible heat engine, which I have over here, into a refrigerator. Because check this out, reversible heat engine means the same system can be used as an engine or a refrigerator without any change to the external environment because it's reversible. So you reverse the engine from engine to refrigerator. And in that case, the output of the reversible engine output of the irreversible engine can be fed to reversible refrigerator. And check this out, work irreversible is greater than work reversible, so I'm gonna have some positive work out, and this clearly eliminates the need for the high temperature reservoir. In other words, if I violate the Carnot principle, I land up with the perpetual motion machine of second kind, or I violate the 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 Kevin Planck statement of the second law. That is not possible. So which means if this violation of Carnot principle leads to violation of second law, violation of second law, that means you cannot violate the Carnot principle. And second Carnot principle is you can have a reversible heat engine, two reversible heat engine with different efficiencies, which means one heat engine would generate more work compared to other heat engine. And what you could do is you could bypass the reservoir completely, which means if the second Carnot principle is violated, that leads to the violation of the second law of thermodynamics. That means that Carnot principles cannot be violated. Now, the next concept is the concept of thermodynamic temperature scale. Now, what do I mean by thermodynamic temperature scale? So, scientists and engineers need a uniform measure or uniform scale or uniform unit to, to compare temperatures. And that is the need for the temperature scale. And this temperature scale should not be dependent on personal preferences. For an example, something cold for me is something hot for someone else. So that's why I cannot have a subjective opinion of the temperature, but I need to have a temperature measurement device which is independent of subjective opinions. So that's why we are going to use a temperature scale that is independent of the properties of the substances that are used to measure the temperature. So I'm going to use this temperature scale. That scale is independent of the properties of the substances that are used to measure a temperature. And this temperature scale is called as the thermodynamic temperature scale. And how do we establish the thermodynamic temperature scale? The thermodynamic temperature scale is established by cascading heat engines. So I will have heat engines that are attached in series. That way I would have, if I TH, after this first engine, which is engine A, I land up with the sink temperature T2. This sink T2 will be the source for the reversible heat engine B that leads to the lower temperature TL or T3. So this concept of cascading reversible heat engine can be used for a thermodynamic scale. And that leads to the definition that we have been talking about is QH is proportional TH and QL is proportional to TL. In other words, the heat capacity of a sink or the source is proportional to the temperature of source or sink respectively. And that leads to the definition of Kelvin scale. So if you have a temperature in Celsius, you add 273.15, that leads to the Kelvin scale, and that is called as absolute temperature scale. So the concept of Carnot principle, the application of Carnot principle leads to the concept of thermodynamic scales. Now, a Carnot heat engine is something similar to the heat engines that we saw, except Carnot heat engine is completely reversible. And when the Carnot heat engine is completely reversible, the equation for efficiency, something like this, can be written as equation for efficiency in terms of high temperature and low temperature. Please note, the efficiency of the Carnot engine is the maximum. COP of Carnot refrigerator is the maximum. So the efficiency of the heat engine is work divided by Q in. So this is QH minus QL divided by QH. That leads to 1 minus QL by QH. And if it's a Carnot engine or reversible engine, this becomes 1 minus TL divided by TH. Now, again, Carnot engine is the most efficient heat engine. So reversible heat engine will have maximum. Now, how do we analyze a Carnot heat engine? So for an example, if and we will work out a few problems wherein we will try to solve heat engine refrigerator. So consider a Carnot engine or a reversible heat engine with the high side temperature at 657, low side temperature at 30 degrees Celsius. So the efficiency is given as 1 minus TL divided by TH. But please note, these temperatures must be in Kelvin. So what it means is you should be doing 30 plus 273 divided by TH, which is 652 plus 273. And when you work out this ratio, this happens to be 7. So this engine is 67% efficient. And if the heat input, so efficiency, is work divided by Qn, now the efficiency is 67%. If I want to find out the work done, so I will divide this by 500, and that gives me the work as 164 kilojoules. And I'm planning to work out a few problems. So this is the first problem. If I give you a Carnot engine, you can find out the efficiency. Now we talked about the quality of energy, and one thing that I want you to note, that higher the temperature, higher is the quality. Now, in other words, as the temperature goes up, 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 the efficiency of the Carnot engine increases. So I want you to note here, if the high side temperature is 350 degrees, the efficiency of the Carnot cycle is merely 13.4. If the high side temperature is 925 degrees Kelvin, the efficiency is 67%. So what it means is, as the temperature is increasing, the efficiency is increasing. That leads to the observation the quality of energy is increasing. So one thing I want you to note, that you cannot use degrees Celsius for calculation, because the ratio in Celsius is not same as ratio in Kelvin. How do you increase the efficiency of the Carnot engine? The efficiency of Carnot engine, you can increase the TH or lower the TL. So you can make TH go higher or have TL go lower, and that would increase efficiency of Carnot cycle. Now the next natural extension is clearly the Carnot refrigerator and heat pump. The concepts that we discussed so far, they are straightforward, can be applied in a straightforward fashion in a Carnot refrigerator. If you have a Carnot engine and you reverse it, it becomes a Carnot refrigerator. So the equations for the COP of Carnot refrigerator is given as this, and equation for the Carnot heat pump is given as this. And recollect, this equation is also based on the same principle, desired effect divided by input. In the case of refrigerator, desired effect is QL divided by W. In the case of heat pump, the desired effect is QH divided by W. Now, when that happens, you have QL, QL minus, sorry, QH minus QL, QH, QH minus QL. So these are the the statements or equations that we'll use when we will work out the problems. Now remember this, just like engine, irreversible refrigerator is the most efficient. So most efficient, which means highest coefficient of performance. So reversible refrigerator or reversible heat pump is the most efficient or the highest coefficient of performance device. And actual refrigerators or may approach these values, but they will never reach them. So this is something that you want to remember. COP of heat pump and refrigerator decreases as the lower temperature decreases, and these are the fundamental concepts that you should keep in mind when we work out the problems. So for an example, here is a simple problem wherein we are looking at the heat pump. So what we want to do is we want to heat the house. The outside temperature of the air is TL is equal to -5 plus 273. Inside temperature of the house is 21 degrees plus 273. And I want to find out the coefficient of performance of the heat pump. And in heat pump, this is QH and this is QL. The heat pump, the desired effect is QH divided by work done. QH divided by QH minus QL. QH can be written as TH minus divided by TH minus TL. So equation for efficiency can be written as TH, which is 21 plus 273, divided by TH, which is 21 plus 273 minus -5 plus 273, and that will give me a coefficient of performance 11.3. Now the heat that needs to be inputted, I think, is this 135,000 kilojoules per hour. So what is this heat in terms of kilowatts? Heat is 3,600 kilojoules per second. That gives me 37.5 kilowatts. And what I do is, so I need to be very careful. This is COP. So COP is equal to 37.5 divided by the work done, or in this case power. So I would use 11.3, and then I can find out the value of equation for power as 3.3 kilowatts. So here is a simple example wherein we are trying to find out the power required by the Carnot heat pump, and I'm planning on working out few more problems on the heat pumps and the second law, because the latest homework that I have assigned, the problems they deal with solving heat pump and refrigerator and Carnot cycle problems. But my suggestion to you all would be uh, try to solve those problems on your own. Theory questions you should be able to solve. I would encourage you to look at homework 3. Theory questions you should be able to solve by the material that we have discussed today. And I will work out few problems in the next class, which is on Wednesday, that will give you a little bit of confidence on attempting those homework problems. And still you will have 3-4 days to work out those problems. So with this, we are done with chapter 6. And at this point, I would like to answer any questions you may have. So I'm not going to work out the problems on chapter 6, heat pump and refrigerators now, but I'll work out some problems in the class on Wednesday. But at this point, I would like to answer any questions you may have on the material so far. So, and at the beginning of the class, there were some questions. So, if you have any questions, uh, uh, go ahead and ask me right away. Any questions on the quiz?
Professor, I have a question on quiz two.
Yeah, go ahead.
The quiz two, last question. There's one explain the significance of differentiated PDV in case of A, flow process, and B, non-flow process. And I'm not really sure because that equation should be just fit for the non-flow process, right?
All right. You sure you want to know
Mm,
the answer? Because I discussed this in the beginning of this lesson. Again, this is a quiz, so I cannot openly give you an answer to the question, but I will try to put you in the right direction. So the question is, what is the difference between PV work and integral PDV work? So check this out. The equation for work is this. W is equal to PV, which is called as the flow work. Now, flow work, basically, if you look at integral minus VDP, is the sum of net flow work, which is PV, and the non-flow work. So that is what it means by the differentiation between the PV and integral PDV. Now, the other thing that I would ask you to see is flow work and non-flow work. They correspond to the different areas under PV diagram. And I would like you to just look at the PV diagram and find it yourself which area corresponds to the flow work and which area corresponds to the non-flow work, And then you will realize that the equation that we have derived here, the equation that we have derived can be explained by means of the PV diagram that we have shown here. So I'm looking for an explanation wherein you can clearly state the difference between these two works and then show them on a PV diagram. Okay, any other questions?
Oh, by the way, Professor, we cannot open the chapter 6 lecture note.
Chapter 6 lecture notes. All right. So thanks for pointing that out. What I will do is I will re-upload the chapter 6 lecture notes. Uh, I uploaded those 2 times. If you go to files, you should see chapter 6 lecture notes 1 and just see chapter 6 lecture notes. And you are not able to download any of those, either of those.
No, I can't. And my friends checked it too, and he cannot download too. And this is only 269 KB. It's not really big enough for contain more
Okay, so
information.
I don't know what the issue is with the canvas, but what I will do is I will upload. Okay, how about the video lecture? Are you able to download and see the video lecture?
Yes, we can.
Okay, so probably there was some issue with Canvas uploading me the PDF file. What I will do is I will upload the PDF file, and not only that, I will email each and every one of you the chapter 6 notes. So today's notes, I would go ahead and email.
Sounds good.
And I will do that. I will do that as soon as we are done with the class today. Okay. Any other questions, concerns, ideas, doubts? So we are coming towards the end of the summer session, but believe it or not, we have covered quite a lot material. Now, chapter that we plan on discussing is the concept of entropy, and that chapter is chapter 7, and then hopefully we would be able to cover one or two more chapters. Uh, so we can actually talk about work potential energy and gas power cycles. And too bad I'm not teaching this course during the entire semester. But at one time, when I taught this course for the fall or the spring semester, then I was able to go all the way up to refrigeration cycles. So, but I won't be able to cover refrigeration cycles uh, in this summer session. But believe it or not, the material for the refrigeration cycles we discuss in detail in today's class. So if you are really interested in air conditioning and refrigeration and how these systems work, just quickly read through that chapter. So that will give you the background, or that will reinforce the concepts that we discussed in today's class. So, are there any more questions? Any questions about the grading? If you have any private question, You can send it to me via text. So have phone number. So text me and I can call you back if you have questions related to grading. If you are concerned about any part of the grading, please send an email to the grader. His email is sbh89 at asu.edu because he is the one who grades it, and most likely he will try to work the issue out with you. And or if you have any question related to the concept, please let me know and I would be happy to discuss in class. So if there are no other questions, the class is dismissed. I will go ahead and upload these slides onto the canvas and I will email those to everyone as well. So I'm gonna wait here for a couple of minutes to see if there are any questions. If not,